Hello. So I see that there's quite a few people that have come already. So, but I will start maybe at in another 5 minutes, so that the MTech CRS students can join in case the class is there before this. So we'll start at 4:45. Okay. Hello. Can you hear me?
Yes, sir.
Yeah. So let's start the class today. So yeah, before I start, tell me what is the situation? Any doubts? Any questions about whatever has been done in the class or the assignments or something like that? No doubts at all? Okay, excellent.
Hello.
Yeah, hello.
Yeah, in question number 1 of the assignment, should we consider the k arrays to be of same size or different size?
I forgot the question. Can you just repeat the question? What was that? Just 1 second. Just give me 1 second.
I mean, given k sorted list of numbers, merge them into a single sorted list.
No, it can be different size. It can
We
be different
consider
size.
the k sorted list or lists are of same size.
It can be of different size also. Yeah, it can be of different size. It doesn't have to be some same size. But I mean, I assume that things is of same size, and then, oh God. Hello, can you hear me? Hello, can you hear
Yes,
me?
I mean, for the complexity calculation. Yes.
Yeah, am I audible properly or is it not? Am I audible? Hello, am I audible? Hello, hello.
Yes, sir, you are audible.
Okay, but I was unable to hear anything from your side, so I'm not sure what was going on. Okay. Yeah, so in the k sorted things, no, you don't have to assume that they are. It is not. You don't have to assume that all the arrays are the same size. They cannot be of different sizes also. Hello, is it clear?
Yes, sir.
Okay.
I mean, for the complexity calculation.
Yes, for the complexity calculation also you don't need that. Yeah, you will not need that. Even for the complexity calculation also, it doesn't matter whether it doesn't matter whether the sizes are same or different. Okay. Any other questions? Hello. Okay. Okay, so did you guys try to solve the other two problems, the problem that I kind of stated in the class last time? Paushali De, are you there? Paushali,
Hello, sir.
yeah. Hello, am I audible or not audible?
Hello.
Yeah, hello.
Hello.
I can hear you.
Hello. Hello,
Yeah,
sir.
yeah, I can hear you. Can you hear me?
Hello. Sir, I cannot hear you.
Okay. Can the rest of you hear me? Hello.
Actually, now it's fine, sir. But just for sir, for like,
Hello, sir.
yeah, it's fine.
Hello.
Yeah, can you hear me?
So
Yes,
now
sir.
it's
Now I
okay.
can.
Now it's okay, sir. Like it was not fine for like 10 seconds ago, but now it's fine.
Okay, okay. So I think I'm in a different room, and that is what is causing the problem. Just wait. Just give me 1 second. Uh, just give me 1 second. Just 1 second. Hello, can you hear me now better?
Yes, sir. Now I can hear you.
Okay, fine, good. Okay, so so did you try to solve the problem that was given in the last class?
That G to the power K
Yes.
matrix. Is
Yes.
done. Actually, yeah, I thought of that, but not clearly understood.
Okay. If you have not clearly understood, that's perfectly fine. But then when I ask you that you have any doubts or not, then why don't you guys ask me?
No, sir. I thought maybe you will discuss that.
No, I'm not discussing that. Unless you guys ask me some questions, I'm not discussing the questions that have been asked that you try it out or something. What about the rest of you? Has anybody tried this k to the g to the power k thing? Shubir Das, are you there? Shubir Das, are you there?
Yes, but I have not tried.
You have not tried. Okay. What about the other problem that was asked about ordering the things in a adjacency matrix, adjacency list? Did you try that? Okay. I mean, I'm assuming that with your lack of answer means no. Is there anybody who tried those g to the power k? Okay, very good.
Hello, sir.
Yeah, hello. Yeah.
So G to the power K represents number of paths of length K. From if I mean if Gij is power K represents number of paths from I to J of length K.
Exactly. Very good. So if somebody gives you g to the power k, then g to the power k means the number of paths of length k. So for example, if you can see my screen. Hello, can you
Yes,
see
sir.
my?
Yes, sir.
Yeah, if you see my screen, then g square. What is g square? So g square is what? You have this matrix G and you have another matrix G, right? And what is g square Ij? This means that you take the ith column here, okay, the column corresponding to Vi and column corresponding to Vj, and you multiply them dot product, right? So this with this plus this with this and so on and so forth. Okay, now what will be? So this is equals to summation of, right, Vi. See, I mean summation of, I mean if I can write it here, okay, summation of G of I k, some k, and times summation times G of kj, summation over j equals to 1 to n. Right, this is just a matrix multiplication thing that I'm talking about. Now, when is this quantity 0 and when is this quantity 1? So this quantity, see, since the entries are just 0 and 1, so this is 1 if and only if ik is a path in is a edge in the graph G, and kj is the graph path in this graph A, right? So basically that means I k j, the number of ways I can reach j from a path of length 2 is exactly what is this one. So this is the number of paths of length 2 from I to j. And now, okay, one thing we have to be careful here is that this k, right? Like for example, what is GII? So what is GII? Can somebody say what is GII? If I, let me see, let me ask some people. Avanish Kumar, are you there? Avanish Kumar? Akash
Yeah,
Kumar?
GIA zero or
Sorry?
dot degree of the GIA defined as
So
zero
GII is 0, right?
or degree.
I didn't mean GII, I mean G square II. Sorry, GII is 0, right? And GII, G square of II, what is this? What is this?
Means from I goes from number of paths from I to I in one step, in two steps.
It's the degree.
This will be the degree. This is the number of paths that I can reach from I to I in 2 steps. I have to go from there to somewhere and come back. So this is exactly like every edge out of I will be counted once. So this will be the degree of I in Vi. Okay. Okay. Now there are of course then I had asked questions like this G is cube and all. Then think in this direction. For them, but so by that definition, GK. I mean, note that here, this basically means that you don't need to use different paths. It's a walk in some sense. It's not a path. It's a walk of length 2. So GK IJ is the number of walks. Walks meaning it's a path where you can reuse edges.
of length k.
Of length k. Number of walks of length k from I to j. Okay. Good. So this is basically, now I doubt how many people have actually tried the other problem of adjacency list, and so I am not going to discuss that one at all. And the other thing is that there has been I think a message been sent, right, that there will be 2 tutorials, one on Saturday and one on Monday, both from 3 to 5. So please be there. It is not a lecture, it will be a tutorial. So if you don't have questions or if you don't have doubts, then possibly after 1 or 2 tutorials, it will be completely stopped. If you have doubts, if you try to have doubts, then we will continue with that thing. Okay. And we will really encourage you to come there, clarify your doubts, try some problems, discuss some of the problems, and so on. Okay, so today, I mean,
Hello.
yeah, hello.
So in that other problem where we have to sort the adjacency list,
Yes.
can we do it using counting sort?
You can do it using counting sort. That's a very good point. You can do it in using counting sort, but then you will need to. How much time will it take?
So sorting each adjacency list will be like for each of them would be the degree, and then the summation of the degree for all of it will be the summation of the degree. Then that will be of order.
Okay, so to
I mean the number of
solve,
edges.
how much does a counting sort take? Let's try to think of it. If I give you an array of size k, where its elements are from say 1 to n, okay, it's an array of size k, array A of size k, and each element is from 1 to n. So counting sort will take how much time? Can you tell me that?
I don't know.
It's order
Degree of
n,
n.
right?
Yes.
So now if you sort the adjacency list, right? See, this one has degree d of 1, right? The next one has degree d of d2 and so on and so forth, right? The degree of 246, and similarly this one. So each of them, if you use counting sort, it would take n steps, right? Right.
Yes, sir.
And then
Yes.
there will be n of them, right? So how much will counting sort take here? Yeah.
Order of degree.
Which one will take order of degree?
The counting sort will take for each vertex we are exploring the number of adjacent
2n.
vertex. So
Will it take 2n?
Okay. Okay. There are two confusions here. Okay. First of all, again, back to this previous thing that I was asking. If I have given you an array, okay, of size k, but each element are from 1 to n, how much does counting sort take? Note that counting sort takes with theta n, not theta k.
theta n.
Okay, theta n. Okay, right? Now here, what we have is that each adjacency, this one, each such array is of size degree d1, degree d2, and so on and so forth. But they are all we know is that they are coming from a set of size
Set of
n,
vertex.
set of the vertices, right? So set of size n, v1 to vn. So sorting each one of them will take how much time using counting sort? N, right? Not degree, not d1, not d2 kind of stuff, but n, right? And then how much will it take the whole thing for? Somebody told 2n. Why will be 2n? The n for this one, the n for next one, the n for the third one, n for the fourth one. So how much time will it take?
N square.
N square. So counting sort will take theta of n square. Okay. Fine. I mean, what would have been the normal merge sort take? Normal merge sort would have taken not order of n, but would have taken order of n log n each of them. So normal merge sort would have taken theta of n square log n. Okay. So counting sort is an improvement, no doubt about that. But my question was that find an algorithm to do it in order n steps, not order n square, or sorry, order m plus n steps. My question was find an algorithm of order n plus m. Now note that m can be n square or slightly more than n square or something like that, right? Sorry, m can be slightly less than n square. So this can be much better than order n square. Okay, so this was the question that was asked. So yeah, so if you have thought about counting sort, you have improved it from merge sort, but it still not comes to the complete optimal. Okay, is it fine?
Okay, sir.
Okay, good. Okay, so today we will be doing this depth first time. So we are talking about the traversal algorithm. We will be doing the depth first search algorithm. So what is depth first search? It is like if I give you a graph, I mean, this is the first time explaining a very high level picture, and then I will give you the algorithm also. Okay. So depth first algorithm would be like, I will first try to, I start from some place, okay? So I start from here. Then I just keep on going. I try to, it's like, as I told you the analogy with learning, right? It is when you take on one subject and learn it everything, and then you go to the next subject. So if to start from here, you go to the next one. Okay, so next one is this one. So at that point you are here. Okay, then you go to the next one. Then you go to the again the next one. You can look, you're just running as much as you can. Then you go to the next one. At this time, when you are here, at this time, what will happen? At this time, you say that, okay, now this one does not have any other unmarked, I mean, not any other neighbors that is not already visited by me, right? So in some sense, I would say that, okay, so that means here I can say that this thing is done. This is done, okay? And I move back up. So maybe I should have used a different color kind of stuff. Let me say with it. I was going down from here, okay? I'm going here, then here, then here, then here. Now when I'm here, then after I'm done, I moved up, right? Okay? To the previous one that I was there. At that time, I look at this vertex. And then, okay, does it have some more neighbor that I have not marked? Well, yeah, so there is this vertex that is not marked. So I go down and find out this. Now when I come here, then it says that this vertex does not have any new result, new thing, right? So it will mark this one up and go to the previous one. Now when I'm here, okay, back to this. Here I'm asking, is there any other neighbor of this that is not marked? So it's like, is there any other subtopic that I have not studied? So no, I've studied everything. So that means this is done. So all the edges that kind of can be reached through this point has been taken care of, right? So I mark that one and go back to the previous one. Then I look at the previous one and say, okay, here is you. Is there anything that is not marked? Yes, I can go here and this is not marked. Then I can go the same thing, right? I can go, is there anything that is not marked? Yeah, this is not marked. Is there anything one that is not marked? Yes, there's this one that is not marked. Is there anything one that is not marked? Yes, this is not marked. And again, at this time, I will find that when I am in this vertex, I say that, okay, this vertex doesn't have any new neighbor that is not marked. So I will go up. Okay, and then I say, okay, now in this vertex, is there anything that is not marked? And the answer will be yes. I can go up to here and make this one. Then at this here, when I'm here, I'm asking, is there anything that is not marked? So I could have gone down this road. But then after going down this road, I've seen something that has already been visited by me. This road is not useful for me. So this is also, it doesn't have any neighbor that is not marked. So I will declare this one also has marked. And I come back to the previous one. Then, okay, by the way, I must have marked this one previous. Then at this point, this vertex will be told that, okay, this vertex is already visited everything. So I will color this one. And I will move to the previous one. Here also I will see that, oh, this vertex doesn't have any other new things. I will go this way. And I go up to this. At this point, I see that, okay, is there anything that is not marked? Yes, this is something that is not marked. And then I color this one up and go back. Then again, is there anything here that is not marked? Yes, I can go here and mark it. Okay. Then is there anything that is not marked for here? See, I could have gone down this path, but again, this is marked. I could have gone down this path, but again, it is marked. So that means this doesn't have anything that is not marked. And so I mark it and go back to the previous one. At this point, this one also has nothing new to offer. So this is marked. I go back. I mark this one back. I go back. I mark this one back. I go back. I mark this one back. And we are done. Okay, so this is the high level picture of what happens in our DFS algorithm. Okay, this is how we expect to traverse the graph. Okay, now note that there is one interesting thing that is there. Look at the edges that have been kind of traversed or that have been used to find out something new. Which were they? Maybe I will use this one. So there, this one, then goes this one, this one, this one, this one, this one. Note that this set of edges, okay, is the spanning tree of this graph. The set of edges that was used to find out or find out some new untouched vertex gives us a spanning tree of this graph. Sometimes it is called the DFS tree. And okay, and the rest of the edges, for example, this edge, and this edge, they are the non-tree edges, and they also have some structure. We will see what the structures are. We will see maybe in the later in this lecture today only. You will see some structures that are there in this graph. Okay, so this is the basic DFS search traversal algorithm. Now, if I have to give this whole information to a computer, if I have to write a program for this, I have to give a line-by-line instruction. I have to tell about some kind of a bookkeeping. So for example, when I have come here and when I am here, I am done with this, I am supposed to go back to this one, not to this one, right? Not to this, but to this. When I'm here, I should go back to its kind of, you can think of it in some sense, to its parent, the place from where I've come back. I should go back to that. How do I keep a tag on that? Okay, all of those instructions have to be given, right? So is there any doubts about this thing? Is there any clarification that you need? Okay.
So this is for connected graph only?
Yes, this is for connected graph only. So if you start with the vertex, okay, I mean, it is not for a connected graph, it can be run for any graph, but it starts from a vertex and it kind of traverses only the connected component, that connected component.
Okay.
Okay. Now you can of course change it a little bit to say that okay, then you start from another vertex in the other component and do another thing there. So in that case, you'll get a forest out of it. But whatever we are going to describe is basically for a single connected component. Okay. Any questions other than this? Any other doubts? Okay, very good. If you don't have any questions, then no problem. That's like great news. But if you have, I will ask people about how to do some kind of a finish this process or something later on. Okay, anyways. So for giving the instruction to the computer, one thing that we will use is a kind of a data structure. It is called a stack. So what is a stack? A stack is basically a data structure that it's called first in first out, or first in last out, or last in first out, whatever that's called. Last in first out. So main idea is that if it is a stack, meaning I say I have this set of A, B, C, D, E, F. So it's like I can put them in a stack. I put A first, then I will put B, then I will put C, then I will put D. Now when I take something out, I will not be able to take out A or B unless I have removed C and D and then C first. So the first thing, so it has two operations. Okay, it has two operations. It's called a push operation and a pop operation. So push operation, what it does is that it will basically push an object inside. So I can say, okay, push A, meaning I'll put A inside. Then you can push B, then it's a put B. Then you can say push D, then put D inside. Then I can say pop. Pop doesn't take anything. So pop just, once I call the pop, it will just take this last one out. Okay, it would return the topmost where it is D and will remain the D from this one. Okay, then if you ask another pop, this is what will return will be B, right? And B will be removed from it. And when I return again pop, then I get A, and again I will remove from. So if I at this point, if I do another pop, usually it is assumed that now if I ask a pop, it's an empty stack, so I should get some kind of a empty symbol out of it. So it's like saying that okay, there's nothing else in this stack. So it's a stack of books in some sense. If you have a stack of books, then the only thing that you can do is that you can put things on top of that. And if you have to take them out, you have to take the topmost out first. Okay, so last in, first out. Because the thing that goes in last is the thing that comes out first. Okay. Any questions here about this particular data structure? Okay, so if there is no questions, then let me then try to explain the DFS properly using the an example using this stack data structure. So I will be using the slides now. You can see my slides.
Yes, sir.
Okay. So I will do this thing on this graph. Okay. So this is the graph that is there, and I have the stack beside me. And I start from the vertex A. Just like I pointed the other thing, the first thing you do is that you take this A and mark it. Now, what is the marking means? You put it within A. You mark it in with the color red and mark it with, put it in stack A. Then you go to its next one. Now you can ask which one is the next. Doesn't matter. You can look at the adjacency list and go to any of its neighbor. We don't care. Okay, so maybe that is B. But as soon as I visit that B, I will push it in this stack, right? Now, by the A is a special color because A is therefore colored red. But you can see that B has got a new color. So as soon as we visit a B, a new element rather, it gets a different color. So that means it gets a color marked. Okay. So now at this point, the next thing is that, okay, does B has a neighbor? So, okay, so how do I know that I have to talk about B? Because that B, so I will always look at the stack beside it, okay? And whichever is the topmost object, I will ask, is there a neighbor of that topmost object? So this topmost object is B, and is there a neighbor of B that is unmarked? And the answer is yes, there is this E that is unmarked, and I visit that E, or push it inside the stack and color it. Then again, you look at the stack and look at the topmost element, which is E, and ask it, does it have a element, a neighbor, right? And this, see, as soon as I find a neighbor, what I do is that I will, the E has a neighbor, right? E has in fact more than one neighbors actually, that is unmarked. I pick one of the neighbors, then push E back in, and then push the other one. So E can visit C, and then C gets popped, E and C then get pushed into the stack. At that point, we are in this C, and I ask, does C has a neighbor? Now, what will C will go to its next neighbor, and the C's neighbor, the first thing in C's neighbor is B. It goes, it looks at in the adjacency list, but the B is marked with a different color, right? So C knows that, okay, although B is my neighbor, that B is kind of not useful because that has a different color. It has been already been visited. So there is this gray color. I don't know whether you can see this one, but this particular edge has been marked gray. It has been visited. This edge has been visited, but it is not contributing to my to the edges that has helped me to find a new one. So at this point, we don't do anything with the stack. Again, we look at the topmost of the stack, which is C, and we look at C, and we go to H. At this time, I look at the topmost thing of H, topmost of the stack. Now, H does not have anything new. So what do I do? So what I do is that I just mark H with a different color, which means that H has been done with. There's nothing to be done with H. So all the vertices that would have been reached from H, okay, has been taken care of. Okay, and H has been popped out from the stack. Now the stack, see, magically inside the stack, you have the last one is C, right? So I look at the last one, which is C, and I say, okay, does C have something new? Again, C has not something new because C has already been taken care of, right? So we can also pop C out and mark C to be done. Then you go to the top again. See, now there will be a confusion. You can think of why not go to B or something. No, we don't go to B because we have to look at the stack and go to the E. And E is exactly from which I have reached C, right? The top of the stack is E. I go to E and ask, does E have something new to offer? Yes, E has F. So I again put F back inside. Then I go to D from F. Again, at this point, I realize, ask D, does this have something new to offer? First, it says, okay, D has a H to A, but it is marked. Not good. D has a H to B, again, it is marked. D has a H to E, that is also marked. So at this point, D realizes that all these edges are marked, or all the edges lead to vertices that have been either been visited or are or completed, right? So at this point, we pop D out of the stack, mark D done, and that's it. Now we go to the stack again. Look at the one that was the top of the thing, file, which is F. See, note that magically we don't have to remember where D came from, because the stack is remembering it for me. Okay. So stack, we go to F, and from F we kind of say that, oh, okay, is there something new, and assigns G. From G, is there anything new? Okay, G has an H to E, but that's the mark. So G doesn't have anything new to offer. So G will be popped out from the stack colored. We go back to F, because F is the topmost. We realize that F doesn't have anything new to offer. So F is marked out, popped out of the thing. We go back to E. At E again, there's nothing else to offer. We check that all of them are done. Okay. And we go to, we mark E. Then we go to B. We don't have anything B to offer. We go to A. And A, again, we realize that A doesn't have anything new to offer. So A is popped out. And that is the end of the stack becomes empty, and we are done. Okay, so this is basically what we do. Look at the red edges. The red edges gives us the DFS tree. So if you have to write this pseudocode, how will you be writing? Okay, so we have the stack S, and we have the two things. Okay, you have to push some element S X into the set S, or you can pop the last element out from the S. So this is the pseudocode, and the simple one. So we go over all the vertices. We initially color every color to. So color is some kind of a, you can say, an array. Okay, we have an array when every vertex, the V1 to Vn, gets colored to start with, and they are all gray. Okay. You start with that vertex V, which is given to you. V is the vertex from which is DFS starts. You start with pushing that vertex V, and you continue till the time that the stack S is non-empty. Okay. As long as S is non-empty, all you do is that you take the topmost of S. So you take U, which is the pop of S. Okay. If the neighbor is empty, then you color it to be green. Okay. Else, what do you do? Else you take some W from the neighbor of U, color that W to be, if the color of W is gray, meaning if the W is still not visited, then you color that vertex to be blue. Okay. From the neighborhood set of U, you remove W. Okay. So how can you do that? If it's an adjacency list, you can always think of that I will look at the last thing, right? I can always start with the, one second. Yeah, so if the, when the, when I'm working with the adjacency list and I have a U in the neighborhood, I can look at I can always start with the last one. Okay, so if the last one is W, I can remove the W by kind of ending my array over there. I can always shorten the array from the last. And this is what we can do. I can remove W from the neighborhood of U, then push U back in, then push W U in, and you select this thing. And this is all that you do. Okay. Is it fine? So basically what is happening that when the neighborhood becomes empty, I mean, once I visit something or I have already went along an edge and found out that there is that neighbor is already marked or something like that, I remove it from the neighborhood. So when at the end the neighborhood becomes empty, that is the time when I kind of am done with it. In my previous one, basically all I do is that, I mean, the finally coloring this vertex green is done by that, right? We color this vertex green, and when you visit something, you are colored blue. So you have three colors. Gray meaning that vertex has not been even reached once. Blue means the vertex has been reached, but it is not yet done. It is not yet complete. It is complete, and some operation is being done on that. And but green means that the vertex has been done. So this is the pseudocode of the DFS.
Sir, what is it? Select UW.
Select UV is for if you are looking at the DFS tree. How do you produce the DFS tree? So UV is the edge that will be in the DFS tree. Okay.
Spanning tree.
On the spanning tree, the tree that will be formed by the So here the red tree, the tree formed by the red set of edges.
Okay, sir.
Okay. Any doubts?
Okay, sir. Yes.
Any other doubts? Any other questions? Any other questions? Okay. So one thing that I will leave it for you to go and try to prove, and this is something that you can ask your tutor, TS for that, is give a formal proof of the correctness of the pseudocode. Now I think you all of you kind of have understood that this is correct, but if I had not explained the algorithm to start with, and I've just told you this particular pseudocode, do you think you would have understood what this algorithm was doing? Do you think that you would have understood that the algorithm is actually correctly finding a DFS tree? Possibly not. Possibly not. Just one second. Yeah, sorry. Yeah. So, okay. So try to find the proof this one. See, there is a while loop here, which means that you have to come up with a loop invariant, a statement that would kind of be invariant under the while loop, and it would be, I mean, that will help you to prove the correctness of this whole algorithm. So try to give us a formal proof of this correctness of the pseudocode of the DFS. Any doubts, any questions? No questions whatsoever. Manish?
Yes, sir.
You understood everything?
Yes, sir.
Excellent. Okay. So
Hello.
if you have, yeah, somebody was asking something?
So the traversal won't be unique, right?
No, traversal is not unique. It depends a lot on the, depends a lot on the ordering of the vertices in the adjacency list. Right? For
So if it's ordered, and I chose like for a given vertex, will it be unique?
If you, sorry, I don't get you. So can you repeat once again?
If I have the adjacency list ordered, and if I chose a particular vertex as a source, will the traversal
Then
be
that will be
unique?
unique. There is no randomness here. So this is one thing if you realize this one, that it's an algorithm and it is a deterministic algorithm, right? So that means if you have an algorithm and if you give the input a particular input, it will always output the same thing. Okay. The issue that happens is that the input might not be same because a graph might have two different inputs, right? Two different adjacencies, these might actually be indicating the same graph, and that's why you will be getting some differences in the the non-unique. But if you can somehow say that I am only looking at the ordered list in the adjacency list, then there is only unique way of representing a graph, right? And that is what it will. I mean, this algorithm will be
Okay, sir.
will give you only a particular stuff. Okay. Shiva Kumar, are you there? Hello.
Yes, sir.
Yeah, can you tell us
Hello.
what will be the
Hello.
runtime of this algorithm?
Runtime of the algorithm. Sir, actually, I missed some part of this lecture.
Okay, so you don't know.
I did not hear the algorithm at all.
Okay, fine.
Sorry about that.
Mahesh Reddy, are you there?
Yes, sir. Yes, sir. I'm actually thinking about the question.
Okay.
Give me a minute.
Order what? Someone said something?
Order of number of vertices.
Will it be number of vertices?
Number of edges.
Okay, why will it be number of edges? See, why will it not be number of vertices? Look at this algorithm over here, right? In this algorithm that we discussed, I mean, we have actually touched all the vertices somewhere or other, right? We've literally gone and marked every vertex edge. And this algorithm is what has been written in the.
Yes, but many vertices are, kind of.
Many vertices are, sorry.
Many time it happens that we have checked whether that vertex is marked or not. So anyway, we are, checking for more than number of vertices.
Checking for more than number of vertices. We are even checking for more than number of edges, right? With every edge we have marked, we have checked only at least once.
Yes.
Right? So you cannot expect an algorithm runtime to be less than m. Right? But
yes,
can it be a lot? Can it be m square or something like that?
Some edges are not actually visited.
Which one?
Can you go to the picture?
Yeah.
Like we are from B to C directly.
Yes, this was also visited. Look at this. Consider the case. Maybe let me go back here. Okay. So at this point, okay, I looked at E. E has nothing new to offer. I go to B. At this time, I look at the top of B, and I check what all edges are there. Okay, what all neighbors are there at this point. Note that from B I had gone to E. So at that time, from the B's neighborhood, E has been removed. Right? But from B's neighborhood, C, D has not been removed. So B will go and check for C. And what it will see is that C is not gray. Okay. And therefore it will have to go back. So it is kind of going down this path and then coming back. I mean, in fact, you cannot see it. Possibly, maybe you're using a different, a smaller computer or something. But actually, these edges have been marked actually at some point of time. For example, say here right now, the edge between E to G, I am at G, right? At this time, I am looking at does G has any new edges, and it is looking at G has an from the in G's neighborhood E exists. So G will go down to E, and therefore it would have. I mean, I have a different color for it actually. You cannot see it possibly, but this edge has now suddenly become colored a bit blue. So every edge is being marked or visited at least. Let's put it this way. Is it clear that every edge is being visited at least once?
Sir.
Okay. Yes, sir. But as an upper bound, can you give us some upper bound? Pallavi Datta?
Yes, sir.
Do you have any upper bound?
So we go of B plus E.
But why? Can you give us some idea why? Why is it?
We are visiting every vertex, that's for sure, and like as you said, every edge also. So,
but why are you? How are you so sure that every edge is not visited multiple times? Maybe one edge is being visited a lot of times.
At most twice, maybe.
Why?
Like when we are ending up, like when we are reaching one end point of the edge, we are checking like whether it has a adjacent, like a neighbor which has been already visited or not. And again, as we are visiting all the vertices, we are at some point of the time we will land up to the other end point of the same edge also, and that point of time again we will check that edge only.
But what is stopping you from? So let me go back here. Okay, so here, so I am at E. Okay, not E is not a good idea. Just 1 second. Yeah, say. Okay, so I am here D. I come back to, I look at all these things in D. Then I look at. Oh, I have not done that stuff yet. I mean, what I mean to say is that, say, instead of now going from F to G, if I had gone, I'm sorry, I had to go from F to G, but so basically one edge could have been looked at it multiple times, right? So let me give you an example of this. Okay.
So yeah, that would happen every time we visit one of this vertex, right? Like every time. So for example, let's say we visit E. Hello.
Yeah. Go ahead.
So let's say we visit E. So we started from we started from A, we went to B, and then we went to E. But every time when we come to E, this edge BE is being checked, right? Because we are checking for E's neighbor.
Okay, so first here, so look at this one. I have first done this, then I've gone to here. Okay, then I've gone here, then here, say, then I have marked this one blue. Then I've gone back, marked this one blue. I have come down over here, fine. Then I have marked this one blue, gone back. Then I go back up. Then I come down over here. Okay. And I mark this one red, and then I mark this one blue again. And I go back. Now I check for this one, right? Hello, is this one? No, it has been already been marked. So I have checked it twice already. Okay. So first I checked it, then I checking it again. So 2 times. Then I go back. Oh no, there is actually another edge here. Sorry, I can go down here and I mark this thing. Then this is now marked back blue. Go back. Then ask, is there something new?
Sir, but once we reach to another vertex from one vertex, we are deleting it from the adjacency matrix for that
That is something
vertex.
that we are doing, right? Because we are deleting from this adjacency thing, once a edge has been traversed, once I have from B I have seen C, that thing can be looked at most once. Because when they've gone from B to C, okay, I have looked at the edge BC from B side, then C is removed from the neighborhood of B. So that is not traversed again. It might be traversed from C to B, but again that would be traversed only once, right? Because as soon as I traverse from C to B, I will remove B from the neighborhood of C. So that's why this thing, that this line over here matters so much. Okay, because of this exact thing, every vertex is being looked from one end once and the other end once. So it will be 2 times the number of edges. So I mean, whatever you guys told, that order of n plus m or v plus e, yes, that is the right answer. But this is what I was looking for. That why is it that one edge is not being traversed more than once? And this is because of this line. Okay. Fine.
Hello.
Yeah. Hello. Yeah.
Sir, can we push a vertex more than once? Because in this last line we are pushing whenever we see an edge from
You
U
can
to
push
any
a
other.
vertex multiple times.
Okay.
Okay, because what is happening is that, I mean, like, look at this one, right? Maybe up. Yeah, say see, at this point, E is in the top, right? So how what will I do? I will pop out E, look at E and say, oh, does this E? So E has already been pushed once, right? Then I look out E, does E has a neighbor? No, E has a neighbor, fine. So I have popped up E, found out that E has a neighbor. So therefore I push back E and C again. E then C. Then at this point again C is pushed up. Basically C has been popped out. C, look at a neighbor of B. And C, it is gray, so we push back inside again. Okay, and we keep on doing it. Then again, after some point of time, when this comes back to E, when this is come back to E, again E is popped out. It looked at, does it have a neighbor? And yes, it has a neighbor. So again, E is pushed back in and F is pushed back in. So, and one element can be pushed back multiple times. Okay, but still, the main idea is that every edge, the main thing is that every edge is being looked at twice exactly. One from this side, one from that side. And that is where the main thing of the algorithm lies, the time and time complexity. Okay. Is it fine?
Yes, sir.
Okay. So, so let me now, in another say 10-15 minutes, give you a important application of DFS. Okay. And this is something that is a very standard. So DFS will have a lot of applications, but this is a very simple application. Okay. Okay, so this is what is there. What was the runtime? But don't worry about that. Okay, so we'll. So DFS is of course a traversal graph. It produces a spanning tree. and it has some nice properties in some sense. Okay. So by the way, I should kind of, this is something that you should just, I will let you guys think about it a little bit, that if I draw a graph, okay, so let me draw the tree now, okay, this is the tree that I'm drawing, okay. Okay, this is the DFS tree. Okay, so that means I have started from this node, this is my root node. I had started from that and I produces that tree. Of course, there are some edges that are not there, right? For example, there are edges maybe like this that is not there, or some edges like this, or like this, some edges like this. Okay. Now, is it possible? So the red nodes, red edges are the edges that are not there in the tree. So, but they are there in the graph. And the blue edges are the tree edges. Is it clear? Now, whatever I have drawn, do you think it is correct? Do you think this is a feasible, a possible DFS tree? Anyone? Swarnolipa, are you there? Swarnolipa, are you there? Swagata? Swagata Samsal?
Yes, sir.
Yeah. Can you?
So without, I mean, the acyclic part, it seems to be a possible spanning tree.
Acyclic part. What is the acyclic part? The blue ones.
Hmm.
Yeah, the blue ones is a spanning tree. But do you think this is a? It's certainly a spanning tree. There's no question about it. Is it a DFS tree? Can this?
Sir, this is not possible.
Okay,
this is not possible.
I'm sure some people have found it out. But somebody was asking a question. Who was saying? Hello? Somebody had a question? Hello? Okay, so some people are saying it is not possible. Who was saying not possible?
Sam.
Okay, can you say why is it not possible?
Sir, if you numbering them, then that will be, I think.
Okay, I number it. Okay, let me number it. Okay, so maybe this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. By the way, this number doesn't say anything about. This number doesn't say anything about the order in which it has been found or something. Okay, they're just the numbers.
Yes, but here we have a age from 4 to 5. So that will be the we go by that.
Correct. So let's see. Okay. So this tree is not a feasible. I mean, this is certainly a spanning tree. Okay, there is no doubt about that. But is this tree, or can this tree be obtained by a DFS algorithm? And the answer is no. Why? So say without loss of generality, I can say that, okay, I will start from, I mean, the first vertex that has after 1, the first one that was picked up, or maybe I should remove this one. The first edge that was picked up, first vertex, was 5. Then what does DFS do? DFS will say that in every other, so before I come back to 1, before I can start from 1 again, okay, I would have completely exhausted or visited all the vertices that are reachable from 5. Okay. So in that case, what all things are reachable from 5? Even 4 is reachable from 5, right? So how is it possible that I have not, at some point of time, consider the time when I had left 5. Okay, I have colored 5, colored 4, colored. Note that I must have completed this whole thing, right? This 5 was the first one that I have put in, okay? So, and 4 is in this right side. So I must have, 5 must have been left, or that means 5 has been colored blue before anything else here. Okay, everything else has been colored. Consider the time when 5 was colored blue. At that time, why wasn't 4 looked into? 4 was still uncolored. Okay, so in that case, at this time, it could not have been that 5 was colored blue. It must have been that 4 was colored. So in that case, this edge would have been picked up as a BFS tree, BFS edge, and not just not a non-BFS edge, right? So basically, in a DFS tree, so in a DFS tree, there cannot be a cross edge. Okay, so cross edge meaning this kind of edges. Okay, and edges of this kind, which is going from one among the 2 different subtrees of this graph. There cannot be an edge between them. Is this argument clear?
Yes, sir.
So this is something that is very useful many times, that this tree has this nice property. Okay, so you complete. The DFS tree will ensure that you complete everything before you go to the go to your parent node. You have covered everything that is reachable from there.
Sir, I think I missed it somewhere. Can you just quickly go through this one, sir? Like, why can't this be a DF?
Okay. Okay. So I start with this one, and without loss of clarity, I'm assuming I have reached to 5. Okay.
Okay.
Right. So I mean, I should kind of remove this one. Oh, sorry. Say. Okay. So that means, okay. Now, since this part of this thing has not been, is different from this part, right?
Yeah.
There's no connection in the blue edges. So these edges must have been found out through 1.
Yeah.
Right?
Yeah.
So that means this part should have been only been found out after I have reached back to 1.
Yeah.
Right? I start from 1, I go to 5, I have done some stuff here, I don't know what. Then I go back to 1, and only then I will find this.
Yes, sir.
Fine. So that means 5 would have been colored blue before this area has even been looked into.
Yes.
So consider the time when 5 was colored blue.
Okay.
Okay. When will 5 colored blue? 5 will be colored blue when there is nothing. There is no neighbor of 5 that is unmarked.
Yeah.
But at that time, 5 has a neighbor of 5 that is unmarked, that is 4. So this edge, this red edge is an edge in the graph. Right?
Okay. I think this is the no, I think this is where I missed it last time also. So at first you told that this was not there, right? Like between 4 and 5.
4 and 5, the edge is not there in the BFS tree. It is there in the actual graph.
Okay. Yeah, sorry. I missed
okay,
that.
the whole graph consists of the red colored edges and the blue colored edges, both. The blue edges are the DFS graph, a DFS tree. It's just like here. Just like
yes, sir.
Okay, the red colored, okay, this is the opposite. I mean, here the red was the blue, blue was the red.
Yes, actually, I got that part.
Okay, fine. You understood now? Or no?
No, I get it. I missed it where the red line was there. So now I got that there. Okay. Yeah, it's yeah. Thank you, sir.
Any other questions? Any other doubt? Okay, good. So this is basically the DFS thing, right? So let me quickly go into this thing. Okay, so this is one. So there are only two colored of kind of edges. It's called the tree edges and the back edges. So back edges are this kind of edges. Okay, this is a back edge. The edge that goes to its edge that goes back to its ancestor is a back edge. But this is an edge across, a cross edge. A cross edge is not possible, but a back edge is possible. Okay, so there are only two kind of edges, a tree edge and the back edge. Okay. By the way, this whole thing that we did for DFS, we can do also for the directed graphs. And I can try to run this algorithm quickly over here and basically say this is the directed graph, okay? And I start from the vertex H and you basically do the same thing, just that you go to its neighbor. Note that the previous one that I've done, I didn't use the undirectedness ever. So in fact, you can do the same thing that we have done. Okay, I mean, I don't want to go into this whole thing, but if you want, you can, I mean, you will produce, and you will produce this red edges, okay, and in these edges, okay, you will have these back edges or forward edges, meaning the kind of edges. So in this case, in the case of the graph, so back edges are forward edges. Forward edges are like this. This is a forward edge and this is a back edge. A back edge is an edge that goes back to its ancestor and a forward edge is one that goes to its. Both of them are possible. Okay. Okay, yeah. So of course, you can use this DFS to check connectivity. So in this case, say, here you can see that all the vertices are reachable from H, because it started from H and all the vertices was reached. That is not necessarily the case in the case of directed graph, right? It might be it is not reachable. For example, if the edge between B to A was in the other direction, right? Okay, B to A and D to A, both of them are in other direction. A would not have been reachable, or in fact, or say if I start from A, then none of them would have been reachable. So this is what will help us to. You can write a quick algorithm using this DFS to check all the vertices that are reachable from a particular vertex. Because once you run a DFS algorithm, then you can check whether all of them has been marked or some of them has been left out. Okay. Okay. Now this is something a bit we have to be a bit careful over here. In the case of, just like we kind of argued that there is back edges and free edges in an undirected graph. In the case of a directed graph, that is not so easy. Okay, it might have cross edges also. For example, just like we argued, whatever if there is an edge like this, this is actually a valid edge, because problem is that when I am in 5, I will not be able to check for 4 because 5 is not reachable from 4. 4 is not in the neighbor of 5. So so it is possible that there are such things. then also we have to be a bit think. For example, I mean, yeah, like if 7 was found earlier, then this edge could not be like this. Then so in the case of directed graph, we have to be a bit careful about the direction in which the ordering in which the tree was produced. So in case of, there can be forward edges, cross edges, free edges, and back edges. Now, okay, this is another thing. Now, what happens if there is a back edge? So I continue and I find a back edge, something like this. This immediately shows that, oh, that means there exists a cycle. I have found a cycle. So this is an algorithm using which you can try to find a cycle. If I give you a graph and I tell you, go and find a cycle. Of course, by looking at the number of edges in that graph, you might be able to say that whether it has a cycle or not. But how will you find a cycle? By running but DFS kind of stuff, you will be able to find a cycle. So these are all various applications of the DFS algorithm graph. Okay. And for all of them, the runtime is just a linear time. Okay, now here is something that I will not necessarily prove. I thought that I will do it, but I will not prove it exactly. Let me kind of still tell you the problem and you think about it, okay? And I want you guys to think about it. I will come back on Tuesday and decide it. So say you have got a job in your company, and in that company, you have been asked that, okay, go and schedule this set of 8 jobs that are there. A, B, C, D, E, F, G. But there are some rules. And these are the rules. That A must be done before B and D. B must be done before C, D, and E. G must be done before E, F, and H. And so on and so forth. A set of rules are with there. Can you find me an ordering of the jobs such that all these various rules are satisfied?
Sir, I can't hear you.
Oh, you can't hear me? From when?
You just like you started it. Like there's this work, and there are some rules, and then it stopped after that.
Okay, sorry. Yeah. Okay, good. So there are 8 kind of jobs. Okay, A, B, C, D, E, F, G, H, and there are some rules. And the rules are saying that, okay, the job number A must be done before B and D. B must be done before C, D, and E, and so on and so forth. Your job is to find an ordering in which these jobs can be completed such that all these rules are satisfied. Okay. So this is a problem that you can find applications everywhere. Everywhere. Starting from actual scheduling of meetings to things like scheduling of the IPL tournament, to scheduling of your computers, kind of breaking up a computer program into running it on a parallelly onto various set of computers. How do you do it? Everything has this problem. And this problem is called a topological sort. Okay. So you have a topological structure and you are supposed to sort them out. Now, why topology, why sorting? I will not try to prove it. Of course, you have been given the hint. The hint is that you use DFS. So I would like you guys to go back, think about it, and try to come up with a solution to this. I will discuss this one on Tuesday. Okay, is this problem clear? Hello? Am I audible? Am I audible? Hello.